This is agenda of my talk. I will just provide some short introduction about FHE. Then, as far as we're utilizing MLIR and LLVM, info about this tech. We will talk about FHE lang, we call out compiler and language, and then infrastructure solutions that we utilize to build applications on top of it. So FHE is just the form of encryption that allows us to have computation of encrypted data without having access to the decrypting key and without decrypting it. Usually we consider some Turing-complete basis, and this is why usually under fully homomorphic encryption schemes, we consider schemes that supports addition and multiplication, because with these operations we can build Turing-complete basis over bits, which means that we can evaluate arbitrary function. The story started in 1978 shortly after inventing RSA scheme. And the first question about possibility to have computation over encrypted data we can find in the paper from this year, also from authors of RSA scheme. Since that time, since 1978, the question about possibility to build fully homomorphic encryption scheme was open, and only in 2009, Craig Gentry firstly built fully homomorphic encryption schemes that support all operations. Since that time, we have great progress. We have developed a lot of different, not a lot, but we developed enough different schemes. This is just the most popular, I would say, one that we can now utilize. And interesting thing is that at this stage, we don't have some universal FHE scheme, and all FHE schemes has advantages and some limitations. Here also you can see just a few examples. Schemes, we have more schemes. The same about library, there are different implementations. We actively utilizing OpenFHE Latigo on our side, but there are also other libraries, and depends on what you want, depends on the stack, depends on your needs, you can choose different ones. But unfortunately, development of FHE application is quite hard because of several reasons. One of them, when you build a FHE application, you as a developer, you are limited in the basis of operations you can work with. Performance is still the issue, but we see the progress, and hopefully it will be solved quite soon, because we see some exponential growth regarding performance. And the also important thing is the lack of developer ecosystem. And the question how compilers can help us at this stage, because I think that one of the important part is to simplify development of FHE applications. And this is why compiler potentially can help us at this stage. And as far as we talk about compilers, let's just have some short intro to LLVM and MLIR stack. LLVM is compiler infrastructure, the most, I think, popular one, open source project. And I think the biggest part of modern compilers utilize or build based on LLVM. And usually when we talk about compilers, it works this way, in simplest way. This is simplest pipeline. At the top level, we have some front-end C++, Rust. Then through some lowering, we're building AST, and then we come to LLVM IR, intermediate representation, that allows us to have different optimizations at this stage, and then translate, lower our code on some backend. This is simplest pipeline, and most optimization usually we have at LLVM IR stage. This is the most, I think, convenient part to do it. But the problem with this approach is that if we consider this kind of example where we have some functions that can do transposition of the matrix, and if we try to use it in row, so if we want to call transpose from transpose of the matrix, which should be equal to initial matrix, it will be lowered on something like this. This is the basic example from LLVM. And the interesting thing is that modern compiler based on LLVM stack can't optimize this code. So they will go deeper, they will lower this code, and it's not possible just to eliminate. And this is bad because it's quite simple optimization if we talk it at high level. And to deal with this kind of thing, different languages, different compilers, like Swift added additional layer. For example, Swift added Swift intermediate language that allows to deal with some additional IR, which will be domain specific and which will open new opportunities to deal with these domain specific optimizations. And then more or less the same pipeline, so we're lowering to LVM IR and then we can transfer to some backend, GPU, CPU, doesn't matter. And this level allows us to have additional, as I said, specific language-specific optimizations. But when we can add one layer, why we can't add some amounts of layer which will deal with some specific things regarding to the language. And this is basically what MLIR is. And MLIR is multi-level intermediate representation that allows us to have arbitrary amount of intermediate representation where we can have optimization, some specific optimization on some specific IR. For example, in MLIR, it calls this IR, it calls dialects, and we can have different dialects. MLIR by itself support quite enough, I think, basic dialects, more than 20. It's some kind of basic operations. So inside MLIR, basically we have some ARIS dialect, we have dialect to working with tensors, we have dialect to working with polynomials. And we just can combine these dialects together and then build passes which convert, which do this lowering step by step. And this is interesting approach, and when we talk about FHE, when we talk about FHE compilers, it looks like very powerful because current FHE stack generally can be considered as different layers. And I will explain a little later which layers we utilize where we're building our compiler. But before, let's just consider the first initial approach to build FHE compilers. The first compilers usually utilized this pipeline. They provided some extension for C++, for some subset of C++, and then translate the code from C++ to some library-specific code. The first compilers utilize only one library, and the code was, all compiler depends on one library. Some compilers utilize intermediate representation, intermediate code, but also there are compilers that didn't do it. At the same time, relatively recently, we saw approach based on MLIR stack. This is, for example, HECO project, which utilize MLIR approach, MLIR layers to build FHE compilers. And we can see that at the high level, there are some general dialect, which then go through lowering and come to some domain-specific library. Another interesting project is HEIR, homomorphic encryption intermediate representation. The team from Google working on it. Here, this is mostly can be considered as FHE toolchain. So this is toolchain that can be utilized to build your own FHE compiler. And currently, at this stage, the project supports different dialects, support some passes. It's some passes quite raw and very limited. For example, here utilize secret dialect, which is some generic dialect where we can present FHE, not FHE, some computation of encrypted data. But the problem that now to deal with secret, there is no simple way how to work with packing because, for example, schemes like CKKS, BGV supports SIMD instructions, where we can pack a lot of different values in one ciphertext. And now passes which come from secret to BGV or CKKS required to do specific work from developers, because now it's not supported, let's say, to utilize different arrays, and there is no way how to fully automate or choose different parameters. Now, as far as I know, it's a little bit limited. Another things that on the scheme-specific dialects, at least for me, it's not clear how we can combine different schemes, how we can add support for scheme switching, but guys from Google said that it will be added. And then we can just go to OpenFHE library, some passes implemented. This is a recent picture from her project, and the passes should be actual. And we can go, let's say, from CKKS directly to build OpenFHE code. Again, I tried to play with it, but it's, for me, it looks like at this stage it's quite limited, because you can't utilize some arbitrary computation. It's supported for some limited basis, but it's actively developing project. I think it's the most active project, best of my knowledge, about FHE compilers. We utilizing some best things from HER, HECO, other compilers, but before I will explain our approach, our layers, let's just consider what is the problem for developers. The main issue when you develop FHE applications that you can do a lot of things. So for example, as far as result is encrypted, you can write the code like this. So we can write just, we can just compare A and B, get result, and then have some branching. Instead of it, we need to do something like this. We need to evaluate some FHE-friendly comparison function, get result, and then evaluate all branches. Which means that we also can have some unlimited loops, and all branch will be evaluated. Another things, let's consider some neural network. General scheme, general layers. So we have some input layer, we have some amounts of intermediate layer, and we would like to have some privacy preserving neural network based on this structure. Mostly all computations in neural network occurs in the neurons, and again, mostly it may be presented as two-step computation. At the first step, we evaluate some weighted sum, and then we evaluate some activation function, usually nonlinear function. And if we want to hide input, if we want to deal with encrypted input, it means that at the first stage, we need to evaluate weighted sum based on encrypted input, which looks FHE friendly, because we support, all schemes support addition and multiplication, and it's not too hard to evaluate these things. The problem occurs from the second step, because we need to evaluate, in this case, we need to evaluate ReLU function, which is not linear, and it's not clear how to evaluate it when you can utilize only addition and multiplication. There are three general approaches how, as a developer, you can deal with it. You can try to build some polynomial approximation, and sometimes it works. Depends on the case, but very limited, because building approximation may be quite hard. Maybe you will not achieve enough accuracy with enough performance. So it can be considered as universal scheme, and it's not friendly for, let's say, bit-basis schemes like TFHE. Moreover, for BGV2, it may be more convenient to use with CKKS scheme. Another things, we can play with the packing. We can try the schemes like CKKS, BGV. Maybe we can try to encrypt some additional information about input. It also limited approach, not universal. will work for some use cases, will not work for others. Another thing is functional bootstrapping, also called programmable bootstrapping in FHE, that allows to evaluate based on lookup table, allows to evaluate some predefined function based on lookup table, but also now we have only limited approach to do it. Usually it's limited in basis, and it depends on when you want to evaluate the function on some arbitrary domain, it may be too hard. And it looks like at this stage we need additional layer to solve this issue. And we consider it as components layer, which will provide to developers building blocks for these cases. So it can be considered as some black boxes which developers can utilize. So it may be like, you know, it's standard library in C++, where you can just take and use it and don't worry about internal structure, because building each of them, building sign component, building relu, it's state-of-the-art work, and it may be quite hard. And if you are just developer from machine learning and you are building AI application, you have not to spend a lot of time on these things, and you just need to utilize it from some library. And this is why in our compiler at the top level we call it polycircuit dialect, but the idea is the dialect related to FHE components, where we can have optimization, where we can work with FHE components, and we can do a lot of stuff around components. At the second layer, when we're lowering from FHE components, we call it also secret, like in Heckle, like in Google. It's some extension of Hair secret and Heckle secret. At this stage, we support during the lowering with different passes, we support at this stage packing, and we can determine moreover which schemes we can use. And on the next layer, we lowering the code in the representation in secret dialect, we lowering to some scheme-specific dialect. So at this stage, we have a code, we have intermediate representation, where we can combine different let's say, commands with different schemes. The next layer we consider is the cryptography or math layer, on which we have the math problem related stuff, because all of which is schemes, as any cryptography scheme based on some math problem. Currently, most of the schemes based on LWE or RWE, but who knows, maybe in the nearest future we will have new schemes. And at the low level, we have dialect for FHE computer, for infrastructure solution we are working on in our team. And from this dialect, from FHE computer dialect, where we have some set of instruction, extendable set of extraction, we can also do lowering to OpenFHE, we can do lowering to Latigo. And also we can run it in our virtual machine, which support this set of instruction. And all of this is just the layers, can be considered as MLIR layers. And two important layers, it's scheme-specific layer and cryptography layer, cryptography problem layer. Why? Just because top layers, totally independent. They may be independent from these two layers, and we can fix it now, and we more or less know how it may look. If we will develop new FHE scheme, if we will have new FHE scheme, most probably that top layers will not require some significant changes. But these layers will require changes, and this is why in our approach, when we build these things, we consider these layers as totally scalable, totally changeable, and we believe that it will be extended quite fast. Also, important things that we use LWE layer or in general cryptography layer, because currently if we work with CKKS TFHE scheme based on LWE, we can consider all crypto objects, ciphertext, public key, private key. We can lower it and present it as some LWE objects. And then if we support this representation, if we can lower CKKS to LWE representation, then through scheme switching, we can just represent it as TFHE. It's not too easy, but its approach, it's important to support this approach because it allows to utilize this layer as building blocks. And then we can provide more opportunity. The same to vice versa. Here, just an example of the code on our language. So we support integer types, we support unsigned types, and we support floating float type, but which is represented as CKKS, so compiler can present it as fixed point arithmetic. And this is some extension of Rust where we support calls for FHE components. And based on this code, it's not required from developer side to set any parameters. The only parameters that can be chosen by developers, it's security level. So you as developer, you can say that I need to have 128 bits of security, and then based on the code, compiler will be able to generate the crypto parameters like ring dimension, everything based on the parameters you mentioned. About components layer, this is the most important layer in our case, but it's difficult to build it because it's a lot of stuff, a lot of work, and difficult to build inside one team. And this is why we utilize for it our challenges platform. And based on the result, based on the challenges, we are going to build this components layer. Now, components presented in polycircuit library. So we publish winning solutions in this library, which is open source without restrictions. You can use it as you wish. It's distributed under Apache license. All components presented with after names, and feel free to use. We explained our approach to build this library and this challenges platform in our paper. You can also find it and read if interesting. About infrastructure, we mostly oriented to FHE computer we are building, which can be considered as network of heterogeneous actors. Each actors can provide some subset of instruction set for our virtual machine and different components. And each applications can be considered as some amounts of components, some building blocks, and these components can be delegated to different actors, depends on the requirement from the user who would like to run it. And the control logic of the computer we placed on the blockchain layer, on blockchain network, where we have at the top layer we have applications, then we have some orchestration, verification layer, which is also very important for FHE, and execution layer. And three of top layers placed, as I said, on the blockchain. It's L1 network. And also we have IPFS-based data layer to store ciphertext, to store all data off-chain. And then during computation, application can be presented as some amounts of components or subset of instructions, and then schedule it for evaluation on some of the actors. Usually we can utilize some fallback actors, and it may be one layer of fallback actors, or it may be more, depending on the needs. But anyway, thank you. That's it from my side.